So Menelau's theorem is basically using signed length. So the first thing you need to understand is the idea of signed length, because length is length. So usually if you write a segment AB, right? AB has length 3, AB has length 3. So then you would have said AB is BA. But in this case you don't. You say if A is to the left of B, yeah, then it is positive. If A is to the right of B, it is negative, right? So this is negative 3. So that's the idea of a signed length. Now, given that the triangle is going to have all kinds of orientation, how will this make sense? So the way to make sense of it is that if you have a ratio, so Menelau's theorem is about, right, you have a line. This is not the same as Seva's theorem. There are no 3 lines, there's a single line. So there's a single line and you want to know what are the 3 points it intersects. And so you're saying if this intersects, so let's say the triangle, original triangle was A, B, C, and this is D, E, F. So then it is telling you a rule about how to work with this triangle, how to know that these 3 points are, if these 3 points are in a straight line, they are actually like this, then you will have a certain ratio. So you'll have, going clockwise, AD and divided by DB, notice the order, times BF, and divided by FC times CE divided by EA. And you say that this is equal to negative 1, right? So then the question becomes, how do you get a negative? And that's what this is defining. If F had been between BC, right, then your F, let's say. So in this case, the BF by FC, one of them is going this way and coming back, this term is negative. And these two are positive. So 2 of them will be positive and the third one will be negative. Because in a triangle you can't have one line cutting it, the third side also within the triangle. Right? So as you draw a line, it will always cut outside. So this term, this BF by CF is what is negative. Right, so the only thing is there's also a cute proof for it. And the cute proof involves a line that is through C that's parallel to AB. So let's say this cuts it at FG, so you can call it G. And then you use the concept of similar triangles to put things back in terms of CG. So for example, these 2 triangles are similar because these 2 are parallel lines and this angle is equal to this angle. So then I'll have triangle, let's say AED is similar to triangle CEG. So remember, if it's similar triangles, then in the order of it conveys the ratios that you want. So you want a CE divided by EA, CE and EA. So CE divided by AE, so this is negative of that, is going to be equal to, we write everything in terms of CG. So let's say CG, because it becomes a common line for multiple things. CG divided by AD, which is also good because you got AD also in the equation. Right. So when you work through these, you do similar triangles. This one, then you do similar triangle bigger one, which is this small triangle, and this line is parallel to this, versus this big triangle, right? And then you have a third similar triangle, which is, okay, those two are enough it seems for the proof. So you can use the similar triangles, take the ratios, multiply them out and get the result that you need.